All right, today we are diving into a really powerful idea from computer science, one that promises to bring a kind of beautiful order to the chaos that can be software development. It's a quest for something called higher order harmony. So, let's start with a massive question, one that pretty much underpins our entire modern world. You know, from the apps on your phone to the whole global financial system, how can we be absolutely certain that the code running it all is actually correct? To get to the bottom of that, we're going to go on a little quest. Here's our map. We'll start in the tangled mess of variables, find a really clever higher order solution, check out the workshops where proofs get built, discover a wild connection between logic and programs, and finally, see the amazing harmony we can achieve. Our journey begins with a challenge that seems simple on the surface, but is actually incredibly complex. The chaos that comes from just trying to manage variables in our code and in our logic. Now, the technical term for these is bound names. Just think of the x in a math function. It only really means something inside that function, right? Now just imagine a huge program with thousands of these things. Keeping track of which x belongs to what and making sure their names don't clash, well, that's a massive source of bugs. And this contrast here is really the whole point. On one hand, you've got this messy, manual way of tracking all those variables. It's just begging for errors, and it's a nightmare to verify. But on the other hand, there's the goal, this clean, abstract way where the system just handles all that bookkeeping for us. It lets us focus on the important stuff. So the big question is, how do we get from messy to clean? Well, every good quest needs a hero. And for our story, that hero is a really elegant concept called HOAS. HOAS. It stands for Higher Order Abstract Syntax, and it's a totally brilliant idea. Instead of us trying to build some new, complicated system just to manage variables, HOAS basically asks, hey, why don't we just use the variable handling rules that are already built into the logic we're using? It lets the framework itself do all the heavy lifting. The approach is actually pretty simple. First, you represent your program's binders using the logic zone functions. Second, you just automatically get all the correct rules for things like substitution for free. And the result? You get to focus on proving your program is actually correct, not on all that tedious, low-level variable nonsense. Okay, so HOAS is our blueprint, but a blueprint isn't much good without a workshop, right? So let's take a look at the high-tech environments where these ideas really come to life. These workshops are called logical frameworks. You can think of them as these ultra-precise digital labs for defining and testing logic itself. They give us the tools to build proofs about our programs, and as you can see here, they let us verify their deepest properties to make absolutely sure they're consistent and reliable. And that's really the crucial point. When you combine an elegant approach like OAS with these powerful frameworks, it's not just about being correct. It's about making the whole process feel more intuitive. The big goal here is to make reasoning about code feel natural, not like some clunky mechanical chore. So, armed with these powerful new tools, researchers started uncovering these incredibly deep connections. They found this hidden symmetry that links the entire world of logic with the world of computer programming. For instance, one of the specialized tools that got forged in these frameworks is something called nominal logic. It's a type of logic that's designed specifically for handling bound names. And it even has this clever little feature for creating fresh variables. But that's just one piece of a much, much bigger puzzle. Because the biggest discovery of all is this fundamental correspondence, this beautiful mirror image that was hiding in plain sight, a perfect match between the world of mathematical proofs and the world of computer programs. It's called the Curry-Howard isomorphism, and it is just profound. What this slide is showing you is a direct one-to-one mapping. A logical implication, if A is true, then B is true, is literally the same thing as a program function that takes an A and gives you back a B. A logical AND is the same as a data structure that holds both an A and a B. They aren't just similar, they are structurally identical. The consequence of this is absolutely mind-blowing. It means that writing a program in a sufficiently powerful language is the exact same activity as constructing a formal logical proof. Every correct program is a proof that it works, and every one of these constructive proofs can actually be run like a program. So, what does this deep, incredible harmony between proofs and programs actually give us? What's the big payoff at the end of this quest? Well, the payoff is immense. We gain robustness because we can create verifiably correct software. We gain clarity by simplifying how we even think about code. But honestly, the most important thing we gain is confidence, the kind of mathematical certainty that our systems do precisely what we say they do. And that lets us build trusted systems that can grow and evolve safely. And that kind of leaves us with a final thought. In a world that is more and more built on this incredibly complex, interconnected software, this deep harmony we've been talking about, it's not just some elegant academic theory. It's a practical necessity. I mean, can we really afford for our code and its underlying logic to be out of sync?